Hello, everyone. My name is Martine Lokken, and I'm a PhD candidate going into my 5th year at the University of Toronto, working with supervisors Renee Lojek and Dick Bond, as well as with all of these lovely people listed here. Today, we'll be discussing prospects for studying the anisotropic superclustering of cosmic gas with CMB and galaxy data, in particular from the Atacama Cosmology Telescope in combination with Planck data and the Dark Energy Survey. During this talk, I'll begin with some background on the thermal Sunyaev-Zel'dovich effect and continue on to discuss how we can use this to measure anisotropic superclustering with current data. I'll discuss some theoretical predictions for the signals that we expect to see, and then I'll share some observational results thus far. I'll end with a discussion of the gas-to-galaxy relationship in filaments and superclusters, and then conclude and mention plans for future work. So to start, let's dive into some background on the thermal Sunyaev-Zel'dovich, or TSZ, effect. This is a foreground impact on cosmic microwave background data, which occurs along the line of sight of hot gas. Cold CMB photons inverse Compton scatter off of hot gas in galaxy clusters and cosmic filaments, gaining energy and shifting the frequency spectrum of the CMB along that line of sight. This effect can be parameterized by the Compton Y parameter, which is an integral of the electron number density and the temperature along the line of sight. Maps of Compton Y are thus completely projected. There's no redshift information. A key advantage of the TSZ, in fact, is that it is independent of redshift. Thus far, its main uses for cosmology have been to use it to identify clusters and measure number counts, as well as measure the power spectrum, both of which are useful for various parameter measurements in cosmology. In addition, it's useful for measuring the physics of the intercluster medium, for example, the pressure profiles, typically through stacking. However, the distribution of hot gas around clusters is typically anisotropic, as they live in the cosmic web surrounded by bridges and filamentary structures. Therefore, cosmological and astrophysical information is missed by these isotropic measures. On the right, I'm showing an image from a recent paper by Hinks et al., which shows two neighboring clusters in a pre-merger phase in TSZ data. This is a highly anisotropic system in which the two clusters are bridged by a filament. In general, this localized anisotropy is found throughout the cosmic web on a variety of scales. Filaments bridge clusters, which in turn can chain together to create relatively rare superclusters. These anisotropic structures are sensitive to cosmology theory in many ways, to the overall curvature, sigma-8, dark energy, the form of the dark matter, modified gravity, and the bias of the tracers. And in particular, including anisotropic information adds constraining power beyond that of the commonly used two-point statistics. So when using the TSZ for cosmology, we need to make comparisons to theory. In the HALO model framework, many people have studied how the integrated Compton Y parameter, capital Y, relates to the cluster mass. In general, this relation is Y is proportional to m to the 5/3 for massive halos. However, many studies have demonstrated deviations from this relation at lower masses due to non-gravitational processes like AGN and stellar feedback. And some studies have examined hydrodynamic simulations with particular models of AGN feedback, which can then be fitted and applied to dark matter only simulations. For example, a study from Battaglia et al. 2012 provided fits that are dependent on the halo mass and redshift. Applications of these fits to dark matter only simulations typically treat halos as isotropic. So in this framework, a supercluster might look something like this. Neighboring clusters are being bridged by some groups and individual galaxies, and each of these halos gets assigned some pressure profile that's dependent on its mass. However, the HALO model is only an approximation. In reality, the universe is not discrete, and there is diffuse material permeating the space in between the clumps of matter. In these plots from the 300 hydrodynamical zoom simulations, the halos are shown on the left, the dark matter for the same field in the center, and a Mach Compton Y map is generated from the gas particle properties and shown on the right. So the state of the unbound gas in the intergalactic medium is very uncertain today based on minimal observations, with only some studies only very recently claiming to detect it. Simulations show this state in various situations because it depends highly on the astrophysical feedback models that are implemented in the simulation. So given all of this background, there are some key questions which have to be addressed to get a full description of the anisotropic gas structure and how it relates to the distribution of galaxies and to the underlying matter. Within the halo model, we want to know how the gas pressure profile depends on halo mass and redshift. Are modifications needed at the lower mass end? How far should the gas profiles extend out? Beyond the halo model, we want to know what the state of the diffuse gas is in filaments. And how does the anisotropy of the gas relate to the anisotropy of galaxies and the underlying matter distribution? Combining it all, we are wondering, can these types of measurements provide stronger precision constraints on cosmology? So these are some of the things that my research seeks to address. Now let's dive into some measurements of the superclustering of TSC. Current maps of the TSC are pretty noisy. So for example, in the ACT data from the Atacama Cosmology Telescope, you can only see really the most massive individual clusters by eye. In this particular cutout that I'm showing, I've circled optically identified DES clusters in white. But they're from a particular redshift bin. And for this bin, it's very difficult even to see in the ACT TSC data these clusters that are circled, even though we know exactly where they are. So it's basically impossible to try to identify which axis is the strongest axis of superclustering going out from that cluster. Therefore, we need to identify the axis by another measure instead. And we can do that by using galaxy maps that have redshift information, in particular in data from the Dark Energy Survey. Then we can align the TSC signal along the strongest filament axis and combine measurements by stacking. Let's hone in on the orientation step. So to orient each cluster cutout, we take the DES galaxies, which have both position and photometric redshift information. We divide them into slices of 200 comoving megaparsecs, as shown on the left. Then we project those slices, and for each one, create a flat galaxy number density map. We smooth the number density map at some scale, which allows for a flexible choice in the scale at which we want to evaluate the aligned structure. With a smaller smoothing scale, we can look at near cluster alignments. With a larger smoothing scale, we can look at superclusters. Then the local Hessian matrix of the position of the DES clusters tells us about the field curvature at that point. And we can use the eigenvectors to identify the primary axis of filamentary structure. We can also select for clusters that live in large-scale supercluster regions by examining the ellipticity and the excursion of the field smoothed on large scales. The ellipticity depends on the difference of the eigenvalues, and the field excursion depends on the overdensity at a given point as compared to the RMS fluctuation level. So you can see on the plot on the left, some clusters, white points, live in regions which have both high nu, represented by the circle size, and high E, represented by the arrow length. In some of the following results, we choose to select only clusters which are at locations where nu is greater than 2 and E is greater than 0.3. By only stacking on clusters that exist in those regions, we expect that the large-scale anisotropic gas signal will be stronger. To review, whether with real data, top plots shown here, or simulated data, bottom plots, we take cutouts of TSC data, orient them by the large-scale structure information from galaxy data, and then stack clusters in an oriented way. In this GIF, the blue circles represent the clusters, the gray circles represent surrounding structure, and that gets overlaid in the stacked images. Stacking increases the signal to noise by square root of n, where n is the number of stacked images. After we have an oriented stack like the one on the left, to quantitatively analyze the signal, we use a multipole decomposition. So we can decompose the left image as shown below with the cosine and sine term of increasing n's. So here I'm showing a visual representation of the cosine multipole moments. These are the relevant values in our case, since the images are aligned along the horizontal. So we'll plot this Cm of r function, which is telling us the strength of that multiple as we go out in radius in the image. The sine term is basically a noise component, which we won't show. So let's see what we predict from simulations and theory. I'll be mentioning some predictions from two simulations, the Web Sky and the Buzzard simulations. Without going into all of these details, I'll mention that they're both dark matter only simulations run with a lambda CDM cosmology, resulting in halo catalogs. To make maps of the Compton Y, pressure profiles are pasted onto each halo, down to a minimum mass of 10 to the 12 m-sub. Buzzard, in particular, was used to mock up the products that are specific to DES, so I'll use Buzzard for direct comparisons with the data. These pressure profiles are fits from the hydrosims I mentioned earlier, which work well for high mass halos but are already known to fit poorly to lower mass halos. But nevertheless, as most of the TSV signal comes from higher mass halos, we might expect this to be a decent representation of the field. With simulations, we examine how we would expect the anisotropic TSV signal to evolve with cosmic time. Here I'm showing those expectations for the quadrupole of the Web Sky stack, with Compton Y on the y-axis and distance from the cluster on the x-axis for successive redshift spins. As the universe evolves, clusters become more massive and they heat up, while the cosmic web also forms denser filaments and superclusters. And all of this leads to an overall increase in the superclustering signal as we go from high redshift, purplish blue, to low redshift, red. We can also explore how both the sample of superclusters and the TSV signal in those regions changes depending on the smoothing of the galaxy field. So going from left to right in both the top and the bottom 4 plots, we're increasing the smoothing scale. There's a lot going on here. The key takeaways are that the location of the peak of the profile is pretty much predetermined by our smoothing. But the height and the shape of the profile tell us physical information about the properties of the structure and the strength of the Y signal. So the takeaway from this slide is that these methods are quite flexible to scale. But however, to anchor this analysis, I'll pick a scale of interest for the rest of the talk. A typical intercluster bridge is about 10 to 15 co-moving megaparsecs. So taking this as a radius for top hat smoothing and converting that to a Gaussian filter, we would get about 20 megaparsecs for a full width half max. So the following results will be shown mostly for this scale, 18 or 20 megaparsecs. Finally, with simulations, we can also demonstrate how these measurements are sensitive to the emergence of non-Gaussian structure at late times in the universe. In both of these plots, I'm comparing the results from Buzzard, which is the solid lines, to a Gaussian random field with the same power spectrum, dashed lines. So let's focus in on the blue profiles, which are the ones from the high superclustering regions. The m=2 quadrupole moment is quite distinctive when compared to a Gaussian random field, which is the dashed line. And the m=4 moment is in fact only present in the non-Gaussian field. So that's a clear sign of non-Gaussianity that we can look for in the real data. So given these many predictions from the simulations, which treat the TSV through the HALO model framework, let's now turn to observational results. At the upper left, I'm showing a real data plot of the ACT-Y map stacked on DES cluster locations and oriented by DES galaxies. So you can see the relatively horizontal signal surrounding the central stack cluster, which I've marked with a black dot because it's very oversaturated in this image. The surrounding signal is from all the gas in neighboring clusters, groups, galaxies, and filaments. Then the plots below show the multifold decompositions of these stacks as compared to Buzzard. Focusing in again on those blue high superclustering regions, there's clear signal in m=2. So the blue circles are from the real data. The continuous profiles are from the simulations, just to guide your eye. The blue triangles are also from the simulations, but they're binned in the same way as the data for a direct comparison. You can see that the simulations and data agree very well. On the right, in m=4, there are some hints of non-zero signal in the blue points from the data, but it's a statistically insignificant result. So we can't claim to have detected a non-Gaussian signal in the TSC at this point. To test our various theoretical models and incorporate even more information, we'd like to be able to compare to other tracers of large-scale structure. The next obvious choice is the galaxies, given how much galaxy data we have today. So let's take the plot I just showed from m=2 and blow up just the red part now, which is the stack on all clusters, not just those in high superclustering regions. If we do the same stack, but now on the projected galaxy number density from DES, in particular the red magic sample, we get a similar type of stack, and in fact, a much higher significance. We can then compare the shapes and the heights of these profiles to each other to understand how the gas relates to galaxies in an anisotropic way. In particular, we can measure the anisotropic relative bias. So here I'm showing the two profiles overlaid for visual purposes, and to do so, I've just scaled the Compton Y by an arbitrary factor. So the takeaway here is that they appear to follow each other pretty well, but we will need some more data to measure this relative anisotropic bias at a high precision. Also briefly mention that we're interested in doing this comparison with weak lensing data as well, which would give us a measure of the absolute bias. Luckily, more data is coming. So with the next data release from ACT, which is called DR6, we will have a nearly full overlap with DES data, this outer blue line, as opposed to the deep 5-6 region, which only had partial overlap. So we expect to get over a 3 times improvement in the signal to noise ratio to detect the m=4 signal and thus late time non-Gaussianity, and make more detailed comparisons with the DES galaxies. So stay tuned for that. In conclusion, in this talk, I showed how we measured large-scale anisotropy in the gas surrounding clusters at the 3.5 sigma level, and how this signal is augmented by selecting for high superclustering regions, going from the red to the blue. With expanded data, we expect the significance to increase, allowing for new measurements of how the dark matter, gas, and the galaxies are related in anisotropic non-Gaussian structure. In the future, we will extend these results to the search for evidence of unbound gas in the warm, hot intergalactic medium, which some recent studies have claimed a marginal detection of. We're also exploring how AGN feedback can impact the anisotropic TSZ signal by using the 300 gizmo Simba runs. It's important to understand how much our uncertainties and feedback affect our ability to make cosmological measurements with the TSZ. And finally, I'll be exploring how the signals discussed in this talk are sensitive to different components of the cosmological model, especially to dark energy, by making use of the web sky and the Quixote simulations. Thank you all for listening to my talk.